next thing that we can do on our image is zero padding. And what do I mean by zero padding? So I guess this was in many of your questions, that for instance, if we have the input, which is 10 by 10, even if we do convolution with the stride 1, at the output we are not getting 10 by 10, right? But what if we want to get exactly 10 by 10? Then basically we need to add 0 around it, right? If you add 0 pixels around it, then you're going to expand your edge. Then your filter could go a bit here and there, and then by that one you can just fix the output size, right? So this is the idea of zero padding. If you want to have exactly, for example, the output to be exactly the same size as the input, or exactly half size the input, right? Then you can add zero padding to make the stride 1 convolution exactly the same size, and then you would just do downsampling to make it half, right? Now, one thing that you might ask me, what is the reason that I want to have exactly the same output size as the input? There are a bunch of reasons that we might need, but one of the key reasons is that sometimes we want to have a very good visualization, right? Say I have MNIST, and then I do train 1 convolutional layer. At the end of the day, I want to see what is coming out of this convolution, right? And say that convolution is by stride 1, right? So this means that if I give a 28 by 28 into it, I'm going to get roughly 28 by 28, right? Now, if my filter is, for example, size 3, I don't get exactly 28 by 28. Yeah, I'm going to get 26 by 26, right? I'm going to lose the last 2, right? Because this filter doesn't go to the, like, it cannot scan the last 2 columns individually. Now I can just add 0 around it. By doing that, I can make the output again 28 by 28, and then I can compare the output to the input to see what is happening, right? What is coming out of this convolution, right? And this is a very useful thing, especially when you want to have a kind of explainable model, because you want to understand where is your model looking into, right? So you give one image. This is in particular very important in like medical applications. You have one medical image, and you want to see whether the convolutional layer is exactly focusing on the part that is important or not, right? And then by doing that, you can just look at the output image, and then like you understand here is more bright, here is less bright, so this means that somehow the convolutional layer is focusing on that part, right? So this is one of the reasons, and if we want to do it, that is not a hard thing, right? Everybody, I guess, can see it immediately, that you can add up a bunch of zeros around it, right? So you can add zeros at the right side, you can do it bottom, you can do it left, you can do it top, you can do it all around it, right? And then by doing that, you just expand your input a bit. It's not like upsampling that you are changing the size by factor. You're just adding a few dummy rows and columns, right? And that one helps you to start scanning, right? To get like a wider range for scanning. For example, if I start from here, then I can just scan individually the first column, and then I keep on going, right? So it's going to increase going to add a few columns to my output, right? One thing that you might obviously see here is that you would never go adding more than your filter size 0 around your image, right? Because if you do that, then your filter at some point is going to scan only zeros, right? And then it's obviously 0 at the output. You don't want it, right? So definitely the zero padding that you are going to do is going to be smaller than the filter size, right? It doesn't mean that if you do it, anything going to happen. You simply get 0, again, zero padding at your output, which you don't need to, right? So in practice, you can always do zero padding around it. What we do usually is that, so you can do it like, as I said, like you can do it all around it. And say, for example, you add PR on the right side, PL on the left side, then the number of columns at the output is going to somehow get scaled proportionally, right? Or change proportionally. Say I add PT at top, PB at bottom, then I'm going to have this much rows at the output, right? So again, it's not going to change in the order of a scale, obviously, but it's going to just increase 1, 2, 3 if you need, right? And same thing going to happen on the left and side, right? So if you add PL, PR to the corners, then you're going to get a bit more columns at the output, and this can help you build exactly the number of the dimension that you want at your output, right? So usually what we do is that we just add 0 all around it, right? And because of this, typically what we do is that we use filters which are of odd size, right? 3, 5, 7. Because when you use a filter of size f, you're going to lose f minus 1 different columns and rows, right? If you think about stride 1, right? So you want f minus 1 to be even so that when you just add symmetrically around it, then you get exactly the same size, right? Just a simple calculation. Say f equals by 3, okay? You're going to lose 2 columns, 2 rows, right? Now, if you want to just compensate for that, you just add 1 0 around the whole image, right? Because 2 divided by 2 is 1, right? So you need 2 more columns, 2 more rows. You can do it symmetrically, right? If you use filter size 5, this means that you're going to lose 4 columns, 4 rows, right? Then you can resolve it by adding 2 rows, 2 zeros top, 2 zeros down, 2 zeros left, 2 zeros right? So if your f is odd, then f minus 1 is even. You can divide it by 2. You can exactly add that much around it, right? But if f is 6, then f minus 1 is 5. So you're losing 5 rows, 5 columns, right? And if you want to add it, you cannot do it symmetrically, right? You need to add, for example, 2 zeros left side, 3 zeros right side, right? Which is not symmetric, so we don't like it. Everybody's clear? So this is one of the non-written reasons that you always see filter sizes being odd, right? Because that makes like all of the 0 padding much easier, right? Much symmetric. Now, one thing that you also may notice is that gradually, as you work with this convolutional networks, you see that many numbers are being missed, right? For example, people tell you that your input is 28 by 28, your filter is 5, and your output is 28 by 28, right? But they don't tell you what is 0 padding. But obviously you can guess, right? When my filter is 5 by 5, this means that I'm losing 4, right? 4 by 2 is 2, so I need to do 0 padding 2 to see 28 exactly at the output, right? So they told me that the output is 28. They told me that the input was 28. This is obvious that we are doing 0 padding. And they told me that the filter is of size 5, so they don't need to tell me anymore that I am doing 0 padding by 0 padding around it, right? Sorry, 2 0 padding around it, right? 2 layers, 2 rows and columns of 0 padding, right? So many times people just drop these terms because they are, these numbers, because they are connected to each other, right? But you don't need to confuse yourself. You can always see it from the, like, look at the model. You can understand what are those parameters, right? So, yeah, as I said, like, for instance, if you do know what is a stride, if you do know output and input dimension, if you know filter size, you really don't need to know 0 padding as long as you believe that they have done a kind of uniform 0 padding around the image, right? So now here, this was the example we had. We did this with stride 2, you remember, right? And then when we did it with stride 2, this was the first part we scanned. We jumped here, we scanned this one, but we could not scan the last part, right? All right? Because that was getting out of the image, right? But now I just add 1 column of 0 here, and this enables me that I jump from here to there, right? So I can also scan that one, so I'm not losing the last column anymore, right? And this means that that column information is also being somehow stored inside my output map. Everybody's cool, yeah? Yeah.
Although you still keep the column that you lost before, given that you're doing an aggregate of values, don't the zeros affect the filter's output?
It's going to affect, but this is not really important because it's just like you deactivate those particular weights, right? And again, for the weights, you can again think, I mean, this guy, if you just follow the idea we initially started with, this filter is essentially 1 neuron, right? 1 perceptron, right? And then it's like you are just deactivating two inputs to that perceptron.
But it's the same one, it's the same perceptron for...
No, it's another perceptron with the same weights.
Okay, it's another perceptron with the same weights. So
Right.
if you deactivate those weights in considering the last column,
Right.
doesn't that affect?
No. Yeah, very, very mildly, right? But you want this to be also somehow stored inside your model. So it somehow learns how to treat the edge pixels, for example, right? So you want it to be. Yeah, that's no problem. Yes?
Practically, we usually put the column 0 in the end of the column or in the beginning of the column.
As I said, you typically do it all around it, right? This example is a dummy example, right? And here, because my filter is 2 by 2, I told you, you usually do not do that, right? So you usually have like filter 3 by 3, right? And then if you want to get exactly, for example, with a stride 1, if you want to get exactly the same size of the input to output, what you would do is that you just add exactly one around, all around the image, right?
So usually the pattern length is
The, on each side, exactly, all around the image, right? So it's like you just add a bit of 0 so that you give a bit of room for the edge pixels, right? But what is the exact number? Typically, it's f minus 1 divided by 2. The filter size, minus 1 divided by 2. If you do that, assuming that f is an odd number, it means that f minus 1 is an even number. Then with the stride 1, convolution with the stride 1, going to give you exactly the same size map at the output as the input. Here, what you have one input image, right? One input. And that input, when you do the convolution, if you do it with a stride 1, you are going to lose at the output. Your output is not exactly the same size as the input, right? And then the number of rows and columns that one is missing is f minus 1, filter minus 1, right? Now, if f minus 1 is even, then as long as you add f minus 1 divided by 2, say f is 3, as long as you add 1 0 padding all around the image, right? The problem is solved, exactly. So in general, you usually have f odd, so it means f minus 1 is even, so you can just divide it by 2, right? So that much 0 padding, if you do it symmetrically all around the image, right, then the output is going to be exactly the same size as the input. As long as you think about a stride 1, right? Now, if you think about a stride 2, then the output is half. If you think about a stride 3, output is 1/3, and so on, right? Right? So this is the whole thing you do. And you cannot add more than that. If you add more than that, you basically start to just scan some complete 0 pixels, right? Which is useless. Yeah?
So the pattern length usually between 1 to 2, or
Sorry?
pattern length is usually between 1 to...
Depends on your filter. If your filter is 11, then you can just add up to 5, right? Because 10 divided by 2 is 5. So you just do 5 all around the image. You can do that, right? If you do 11, obviously you are scanning complete 0, right? You can add 10, but adding 10, like 5 to 10, it's not going to improve too much.
But isn't the f is 11?
Yes, you can do that. You can
When f is 11, we add 10 on the side. Oh, but it's double. Okay, no.
Yeah, you are adding both sides, right?
Oh, okay.
Yeah, but you can do that. You can add every side 10, and it still works. No problem with that. But this is not going to help you too much. The main reason that you usually do it is that you want the output to be exactly the same size as the input. And if you do it 10, then the output is actually a bit larger, right? You don't want that.
Okay.
Yeah.
But if we do stride equal to 1, does it really matter? Like if we do 0 paddling or not?
Not really. Many architectures do not do it. But typically people, I mean, like old days, people were happy with working with exactly same size maps every layer. And the reason was because they wanted to just look at that map, see what is happening inside that map, whether the training is really going on or not. But if you drop it, nothing happens. Yeah. North. You got it? No? Okay. Questions? Okay, so if you got no questions, so again here, as I told you, so you are actually using those edge pixels because you are adding 0 to the last column, right? So that is the idea of zero padding. And last thing, now with the convolution, you do know the operation, right? So you're doing the convolution operation on your input map. And that convolution operation, you can do upsampling, downsampling to play with this, right? You can do zero padding if you just want to add a few extra columns or rows to the output. And finally, after doing that, you get one map at the output, right? That map at the output, that Z, is actually a linear combination of the input, and this linear operation was done by the convolution. Like in the basic MLP, you do it by simple linear combination with different weights. Now you're doing it with convolution. It's still a linear operation, right? Once you got that output, you need to add nonlinearity to that, right? And the thing that you would do is that you basically just activate. So what you do, you say you have this filter W, right? And then you have input map X. You basically first do the convolution. If you want, this is not usually the case, but if you want, you can add a bias as well, right? So once you computed all the convolution, then you add a bias to every single entry, right? Yes? Right. Because always think about that example we had, right? So that guy which is going over them is just single perceptron, right? So it has the same bias, right? But this is exactly the same bias for every single entry inside Z, right? Per filter, right, exactly. So we're going to have one bias per filter, but the point is that it's not too much parameter, right? So typically we don't do it, but if you want, you can add it. Yeah, that's not. Now, you do the convolution, you add the bias if you want. Now that you have Z, the next thing that you're going to do, you're going to activate it. It means that you look at the output map, and then you pass every single entry through the same activation function. That could be a ReLU, sigmoid, or anything that you want. Okay? Now, if you do both of these operations, so you do the linear operation, which is the convolution, and then you activate it, this is what we call it, the whole thing. This is what we call it a convolutional layer, right? So a convolutional layer is the guy who is taking the input map, and then it just does the convolution on it, activates that, and gives you one output map, right? Everybody's clear, right? Questions? So if you want to think about this, so this guy, this is your, for example, MNIST image. This is a map of 28 by 28 pixels, right? You can send it over one convolutional layer. So you convolve it with a filter. You might add a bias. Then you get one output. Those outputs are a bunch of numbers, linear combination of all of the pixels, right? Then you do one activation, right? And then you could eventually look at the activated one, the output. And you're going to see that there are some specific things happening, right? Old days, people wanted to see how does convolutional layer understand whether this is 6 or is 1. And then they started to look at the output of that convolutional layer. They see that after training, it starts to give them like some of the convolutional layers, some of the filters are somehow paying attention to the curvature inside the number. Some of them are paying attention to the edges. And they started to have the feeling, okay, this convolutional layer is thinking whether there is a curvature or not. Because if there is a curvature, then this is probably 2, 3, 6, right? These numbers are more likely to happen, right? Whereas if it is very edgy, maybe it's just 1, right? Or 7, right? So they started to just look at that output and see where it's being more focused. Yes?
Is this bias scalar or?
It's a scalar. No, yeah. It's just added to every single pixel of the output. Yeah. Questions? No question? Okay. So now, for the activation, again, you can use any activation that you want. ReLU is a very classical one for the convolutional neural network. So ReLU is like for most visual things, ReLU is fine enough. But again, you can do it as you wish. And yeah, that's going to be the convolution. Okay? Everybody's clear, right? Now, the thing that we did was for one channel. What is a channel? It means that my image is just one matrix, right? when I talk about MNIST image, it's 28 by 28, one matrix, right? But a real image is not just one channel, right? A real image is a multi-channel thing, right? Like, for example, you have RGB image, right? An RGB image has 3 different channels. One of them is red, one of them is green, one of them is blue, right? And then what you see in practice is a kind of superposition of them, right? So the color image that you see, it is something like this, right? This image has a red channel, green channel, blue channel. Those 3 channels on each other, you see it as a color image, right? Everybody's clear, right? Now, 3-channel is just a simple RGB image. Do you know of more channel in any like application? Have you seen these depth cameras? Depth camera, right? You have seen them, right? They have more channels, right? I think that, like the basic one has 4 channels, right? One of them is talking about the depth, right? Like satellite images, some of them have 12 channels, right? Because you take with different wavelength image from one side, right? And it's going to give you the idea not only from the 2-dimensional information, but how deep everything is, right? Because different wavelength have different penetration, right? Right? So you can have more channels. This is for visual applications. For non-visual application, well, you could have as much as you want, right? Maybe you're collecting data from users, right? And then you put it inside multiple channels, right? One layer, one channel is just collecting all information about the surface interaction. The second one is the information you conclude out of background scene, what is happening on the background of the activity of the users, and so on, right? You can add up as much as you want. So in general, you could have C different channels. So you could have one collection of C different matrices next to each other. And if you want to just put them in one object, you typically keep them of the same dimension, right? So if it is one RGB image, red, green, blue channels, all of them are 32 by 32, right? Or 512 by 512, right? When you say I have an image of resolution 1024 by 1024, it means that you have one red channel is exactly 1024 by 1024 pixels. One green channel, 1024 by 1024 pixels. One blue channel, same size, right? So this is what we call a tensor. You might have heard of it, right? And tensor means that you just start to build your arrays in larger dimension, right? So vector is one-dimensional array, right? Matrix is a 2-dimensional array. Then you can make it 3-dimensional, right? You can go for 4-dimensional. That we cannot imagine, right? But we can write it, right? So I have a set of 3-dimensional tensors, right? And all of those 3-dimensional tensors are of the same size, right? And I collect a bunch of them, right? This is going to be order 4 tensor, right? Typically, when you work with images or visual things, you have order 3 tensor, right? But you can go up, and PyTorch lets you do that, right? You can just define the dimension to be 5 times 8 times 12 times 22 times 100 times, and so on, right? You're just increasing the order of tensor, and it's okay, right? You're just nesting arrays inside arrays, right? And as long as you have 2 tensors, they're of the same size, you can do whatever operation you want on them, right? So now, we typically work with order 3 tensors when we're dealing with visual data. And then in that case, this means that we have C different channels, C different matrices of the same size, just stacking next to each other, right? So something like this, right? So you have one map, the second map, third map. You stack them next to each other. This is one tensor with 3 channels, right? Now, the thing is that the kind of data that you usually want to process with your convolutional layer is exactly this form, right? You're going to have multiple channels. It's not just a single channel. It's not always MNIST data set, right? And if you want to just handle this, you can just simply extend the idea of the convolution that we did up to this point to the case with multiple channels. How we can do this? Well, you basically do the same thing as before. Now, instead of having your filter to be just one map, the filter is also having some depth. Okay? It's the same thing, same operation exactly, but instead of thinking the depth 1, which we thought up to this point, we just make it depth C, right? If you do that, everything can just extend to this case, right? What does it mean? Say you have a 3-channel image, right? And you want to do the convolution. What should be the number of channels in your filter? It should be 3, right? Because your filter needs to have one channel, one part for the first channel, one part exactly the same size for the second channel, one part exactly the same size for the third channel, right? And then you put it like this, and then it goes like further, further, and so on, right? So it's like you get this guy. This is a filter 3 by 3. It has 3 channels. And then your input has also 3 channels. It's fine. So I'm going to take this one. I put it on the first part of it, right? Multiply all the weights with the corresponding pixels, add them up, write that on the output filter, output map, right? So here I have 3 channels. My filter should have exactly 3 channels. So you should think of it in this form. So this guy gets multiplied to this part of the image, right? The first channel is getting multiplied with that subpart of your image in the first channel, right? Right? The second channel is getting multiplied with the second subpart of your image in the second channel, right? And the third one to the third subpart, right? And then you get that one, multiply everything, add them up, you write it down as the first entry of the output map, right? What should be the next entry? If I am doing it with a stride 1, I just shift everything 1 pixel right, right? So I just shift everything 1 pixel right? So again, you have 3 channels. Those 3 channels get multiplied with the 3 channels of filter, add them up, get it as one number at the output, right? And you keep on going. Like, for example, if you think about going towards the end of the first row, then you're going to get here. They are getting multiplied, added up, written there, and then you can go 1 down. You keep on going like this, right? So if you have multi-channel image or multi-channel input, you basically need a multi-channel filter. And what is the number of channels inside your filter? The same number as the number of channels in your input, right? So nobody needs to tell you that I am processing, for example, CFAR image, which is an RGB image, and I have filter 11 by 11 at the first layer. Nobody needs to tell you what is the number of channels in the filter. You immediately understand this should be a 3 by 3 filter, 3-channel filter, because the input has 3 channels, right? So the number of channels here should be exactly the number of channels here. Now, what is the number of channels at the output after doing the convolution? 1, right? You're not generating multiple maps. You're just generating 1 map. Everybody's clear, right? Everybody's cool? So if you want to write down again the convolution in this 3-dimensional case, what you would say X and W. W is the filter, X is the data, and W and X, they both have the same number of channels. You see both of them have C channels, right? And then this one is the filter. I am going to do exactly the same operation. So I multiply it with one part of that image, and then I add them up. This is going to be that particular feature I compute at the output, right? Now, that part of the image is exactly the same thing as we had before, right? For rows and columns, right? But for depth, what is happening? The filter has exactly the same number of channels as the input, right? So they're going to exactly lie on each other. There is no problem. So each time, all the channels in the filter get multiplied with all the channels in the input, right? Everybody's cool, yes?
Are the weights for the filters for each channel
Different. Different, right? So here, for example, let me see. So here, for example, is a 3 by 3 filter. You have 3 channels, like, all right? So you have 27 different weights, right? And you're going to learn all of them. So the deeper it gets, the more parameters you're going to get, right? Yes?
So, like, I can understand this as each channel has their own individual filters and their own network, so we just
Right.
populate everything 3 times.
Right. Yes. It's like you have 3 channels and you process them in parallel with 3 different filters at the same time. It's the same thing. But the key point is that at the end, you don't write them in the 3 different maps, right? You just add up all of them in one map, right? This is the only difference, right? So here, this first channel of the filter is getting exactly the same wave convolve with this one, right? But it's not being stored in an independent map, right? Whatever it computes is added with whatever the others compute, right? And then you add all of them, write it in one map. Right, because your output has just one channel, right? So you get the 3 channels. Those filters get multiplied with their corresponding part in the image. Then you add up everything, right? All the channels, right? Questions? Okay, so that is what gonna be a convolution on a multi-channel input, and then, as I said, so the number of channels you're going to have inside your filter is going to be exactly as the same number as the number of channels you have in your input, but your output is still just one single map, right? Your output is just one single map, right? So you can do whatever we talked about before, exactly as before. So upsampling, downsampling, zero padding, whatever you want to do, you do it on all the channels, right? And going to be exactly the same thing, right? No bother in that respect. Now, one last thing. What I am doing, I am getting this image, right? And say, for instance, that image has like 12 different channels, right? And now I am doing the convolution with one filter, which has, again, 12 channels, right? I go over this image, right? Say I do zero padding, whatever, right? And say my image with 12 channels, it has, I don't know, 100 by 100 pixels. If I do zero padding, stride 1, everything fine, then at the output I'm going to get a map, right? And that map is 100 by 100, right? So I'm going to have a single map, 100 by 100, right? I got 12 channels, which were each of them was 100 by 100. It means 12 times 10,000, right? 120,000 pixels. And then I converted it into 10,000 numbers, right? It doesn't sound like a fair trade, right? Because you had a huge amount of pixel, huge amount of data, and I'm just breaking it down into a very compact number of numbers, right? Well, if I do it at the very, very end, when I am very clear about my information, that's fine. But at the beginning, I usually want to extract more and more features, right? So when you, for example, in the MLP, when you process one data, you start with the small data, and you start to go up, right? You just increase the hidden layer size to just get more and more features. At some point, you say, oh, I have so much features, so I can start shrinking down, right? You start to shrink down to get to your output. And all of those features you extract are going to help your neural network to understand what is going on, right? So you want to do the same thing here, but right now with this approach, there's no way you can do it, right? Everybody's clear, right? What I'm doing, what I'm saying, right? So that is not a good idea. How can I resolve this issue? Sorry? I don't want to do that. That's not a good idea. Because there is a reason for that. Because RGB, the pixels, are somehow interconnected. So I want to capture this connection, right? I don't want to just lose that. Use multiple filters, right? So I did it with one filter, I got one map, right? I use another filter, I get the second map, third filter, third map, and so on, right? So you can, in general, do it with multiple filters, right? And every filter is computing one feature map for you, right? Now, if you have 12 channels at the output, you want much more features at the output, okay, that's no problem. Just use 20 filters, right? You're going to get 20 feature maps, right? All of them 100 by 100. The input was 12 maps, so you are expanding, right? Again, you want to increase. You get that guy. You do again convolution on that one. That guy is again 20 channel output, right? And you start doing 20 channel convolution, maybe 100 of them, right? and you are getting at the output 100 different maps, right? You're just expanding the information you had in different maps. You're just breaking it down, separating it into different maps at the outputs, right? So this is the basic idea. So you could have two different filters. Each of them has its own weights. You're going to learn all of those weights at the end of the day. This guy is getting convolved with this one, computing one feature map, right? This other one is getting convolved with this one, computing another feature map, and then you just collect those feature maps together at the output. This is the most general form of the convolution that we do. So in a most general convolution, you usually have multiple channels, k different output channels, and this is exactly the number of filters